Swayam Prabha. Digital India. Educated India.
My topic is automatic segmentation of dynamic and static models based on high-order slow-feature analyzer for multi-phase batch monitoring. The chemical process can be broadly divided into batch process and the continuous process. However, the diversity of products is getting higher and higher, and the different products may be produced every month. And this time, the batch process will be used, because the batch process has higher variability and a lower equipment cost than continuous process. And batch monitoring is a very important issue. For example, the blue line is a normal batch and the red line is a full batch. After this time point, the red line moves away from the blue one. If there is no real-time monitoring, the error will not be known until the batch is completed. This is the waste of the time and the money. So we hope that we can monitoring batches use some sample variables. The batch process generally has several features. The first one is multi-phase, which corresponds to red, green, and blue in this picture. The second one is three-dimensional data, and the third one is a nonlinear process, and the fourth is uneven batch length. In the operation process of the batch, it can be broadly divided into several parts. Take this picture as an example. It is divided into 4 parts. The meaning of the 4 parts will be explained in more detail in further slides. First of all, the first part may be feeding, and the order of the feeding is assumed to be put in A first, then B and C, then finally stirred evenly. However, here comes the problem. The batch is a closed reaction tank. So how does the operator know when it will stir evenly? So it is necessary to wait for the batch to be fully stirred according to experience. So there is usually a rest period in the batch, which is the red part in this picture. After fully steaming, it may not be the best reactive temperature at this time. So adjust a set point to optimize the reaction, but this will return the question just now. How does the operator know that the reaction has been complete? This again can be empirically wait for a complete reaction, though restarting in the less green part. So in a batch, it can be divided into the dynamic part of the blue part and the static part of the red part. However, in the past methods, this problem will hardly discussed in a batch, and a batch was put into a single dynamic model or a static model. But this way, the batch process cannot describe completely. So the best way should be divide the batch into a dynamic part and a static part, and a batch, a dynamic model and a static model respectively. In the past dynamic model, slow feature analyzer is a good method because SFA distinguishes the monitors the dynamic of different frequencies. For an example, X1 is an A plus B, X2 is B plus C, and X3 is A plus C. And the X1, X2, X3 can be extracted from the slow list to the faster after SFA projection. But there is a problem with SFA. SFA approximates the first order differential with a first order difference and describe the whole process. However, in the new process, there may be a high order dynamics. So it is necessary to extend SFA into a high order SFA. To sum up, the questions raise a vote. I hope that the batch process can be automatically divided into dynamic parts and the static parts. And the dynamic part is monitored by high-order SFA, and the static part is monitored by the PCA. First of all, I will introduce how I designed an objective function to automatically distinguish the dynamic part and the static part. Firstly, I assume that the batch process has only one phase and it can be divided into a dynamic and a static part. Therefore, I combine the objective function of SFA and the PCA. SFA hopes to obtain the minima rate of change after projection, and the PCA hopes to obtain the maxima variance. As a result, the objective function of SFA and PCA is subtracted, and the weight of SFA and the PCA are respectively given to each time point. In the beginning, the weight is defined as the reconstruction error of another model. For example, the weight of SFA model uses the reconstruction error of PCA, and the weight of PCA model uses the reconstruction error for SFA. Because the reconstruction error is very large if the static model is used as the dynamic time point. In this way, the static model can be weakened to strengthen the dynamic model in the dynamic part, and the dynamic part can be weakened to strengthen the static model in the static part. In the batch process, if the previous time point is dynamic or static, the probability of the next time point being dynamic or static will be high. Therefore, the weight of the original single time point is extended to multiply by 2 points to make the classification better. But only this still has a disadvantage. This is in the static part, the reconstruction error of SFA and the PCA will be very small because the static reconstruction is intuitively small, and the difference near the static is also small. So it is necessary to add a correlation image. And this correlation image is the standard deviation because the biggest difference between the dynamic part and the static part is the range. Therefore, after adding this correlation image, the dynamic and the static part can be better distinguished by comparing the weight. When distinguishes the dynamic and the static parts, it is by comparing the value of the dynamic weight and the static weight. But there will be a problem. When there is interference, there may be unreasonable classification as shown on the left figure. It is impossible to standardly switch from a dynamic process to a static process, and then immediately switch to a static process in a batch. Based on this, these two paragraphs are unreasonable. The real process should be as shown in the figure on the right. After a certain point in time, the process changes from dynamic to static. If the part classified as dynamic is regarded as 1, the part classified as static is regarded to 0, which can be transferred into the following two pictures. So we need to define another objective function to change the left picture into the right picture. The concept of this objective function is very simple. It is to find a switching point and treat the same size of the switching point as the same features. Therefore, the objective function is to find a switching point, and after changing the features of the last point, change the same size to the same features. In this way, the above mentioned unreasonable classification can be ruled out. However, the above-mentioned methods assume that the batch has only one phase and can just be divided into a dynamic and a static model. Therefore, if it is extended to a multi-phase or multi-models, the objective function can be rewritten as such. This represents arrow batches, and this represents all dynamic parts, and this represents I static parts, and finally, this represents the length of the batch. The above has been able to divide the batch into dynamic and static parts, and then we will introduce the high-order SFA and its monitoring method in detail. In the first-order SFA, it can transfer the original data projection into a dynamic from fast to slow through projection. In this way, the traditional SFA create the T2 of its latent space. But the T2 assumes that the data is accurate and Gaussian distribution. But it is obvious that the autocorrelation of the latent space after this projection is far from zero. And only the autocorrelation of variable in some latent space approach zero. Therefore, only this variable can express T2. In the first order, SFA cannot be fully described. Then continue to use the second order SFA until the autocorrelation of all variables in the latent space approach to zero. Then this variable can be attributed the T2 and stop continuing with high order SFA. In high order SFA, it is assumed that the data can be cut into J orders. Then there will be J control limits, and normal data requires all T2s to be belong to the control limit. It is not normal if one of the orders T2 is out of the limit. A simulated batch process is simple design here. This training data has 10 batches. The red dotted line is the switch point of batch. Before the switch point, this dynamic is followed. And after that, another dynamic is followed. And the red slow line is the end of the batch. First, divide the batch into 5 equal parts. On average, the following two pictures show their weight. Afterward, you can find that ML, HO, SFA, PCA will start to automatically integrate and classify. When there is too little data in a certain part, the part will be removed, like this. And when it finally converges, you can see that ML, HO, SFA, PCA distinguishes the dynamic and the static part very well. Compared with other methods, firstly is sub-PCA, which uses K-mean to classify the projection vectors at each time point. But it can be found that the red area is very unreasonable because these two areas is in two phases, but they are not in a same label. Then there is WNSSPP, which uses smoothing windows to classify, but it can be seen from the figure that the classification is not very good. A round batch was made here, and the real dynamic relationship was adjusted. Then the blue line is the normal data, and the red line is the fault data. It can be found that the error starts in the phase 2 until end. In phase 1, HO, SFA, and the PCA did not monitor errors because phase 1 doesn't have the errors, so this result is reasonable. In phase 2, HOSFA and the PCA can find the fault, and this result is very good. And here is also using a real inductional process to prove that MLHOSFA PCA is more effective than other monitoring methods. Here is a real PVC synthesis process with a total of 4 variables, as shown in the figure. And put this process into MLHOSFA PCA, sub-PCA, and WNSSPP for comparison. The above 3 pictures are the classification results of the different methods. The blue line in this picture below is the normal data, and the red line is the fault data. This fault data is due to the fact that there are too many initial carriers in the batch, and the process is out of control and needs to be adjusted manually. The engineer discovered and stopped to adjust at the time 30 and returned the wrong batch at normal at time 80. Putting this error into these 3 methods and compare their FAR and FDR, it can be found that the monitoring effect of MLHOSFA PCA is the best. And here is a summary. HOSFA is an improved SFA that involves multi-order differentiation to completely discrete the process. MLHOSFA PCA divides batch data into the dynamic part and the static part to improve monitoring efficiency. MLHOSFA PCA completely discrete the process without kernel function. This is all of my position. Thank you for your listening.